everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll continue discussing Laplacian matrices. In the previous lecture, we defined what exactly is a Laplacian matrix. In today's lecture, we'll see an example of a practical system which can actually be described using a Laplacian matrix. We will also discuss some more of its interesting properties. So let's get started. Consider the electrical network shown in this figure. When we're trying to represent this electrical circuit in the form of a graph, the nodes that are the junctions that are shown here become the nodes of our graph, and each branch becomes an edge. The branches shown here become the edges. Now, we know that any electrical network must satisfy Kirchhoff's voltage and current rules. Now, let us try to apply Kirchhoff's current rule. Let's try to apply it at the kth node. Right, for the kth node, Kirchhoff's current rule says that all of the incoming and outgoing currents add up to 0. Meaning, let us take any node K. Let's consider the pth node in the network. Then for the pth node, let IPQ be the current from a node P to a node Q. And we're summing up all of the currents coming into and exiting node P. So we vary Q over all of the branches that are connected to this particular node. According to Kirchhoff's rule, all this summation has to go to 0. Of course, we can write it further in terms of the voltages given as this. Summed over Q. VPQ is simply equal to VP minus VQ times the conductance CPQ. Again, this must add up to 0. The conductance obviously is nothing but 1 by the resistance. Now we can write up this expression for every pair of nodes in the network, for every node in the network. While this summation adds up to 0, of course, we have a current source here, as we can see. Now, when we apply the Kirchhoff's rule here, what we would rather get is something like that. Let's write it for the ith node. Now, we can keep aside this incoming current on one side and then the rest of the currents, rest of the branches separately. Then it will allow us to write this expression for the, this should be the 8th node, which is shown here. Now, for this 8th node, Kirchhoff's rule gives something like this. Now, again, the summation of I, A, Q, where Q varies over the network, this summation becomes equal to I naught. Similarly, for the Cth node again, there will be one branch here, which will also have a non-zero current. Again, while writing the summation, we can separate out these branches. And we write it in this manner. For the Bth node, IBQ, where Q varies over all the branches connected to P, should be B. IBQ. This summation is minus of I naught. Why? Because here the direction, whatever is the direction here, it's the reverse direction here. So we write it as minus I naught. So why have we separated out these two branches here? Well, the reason why we have separated out is as follows. If you look at any other node here, any other node shown here, we see that we can relate it to only the branches pertaining to these set of nodes, or only these branches come into picture. And no, they're not connected to the external source that is there. Similarly, when we write the Kirchhoff's equation for the Ath node, what do? We separate out these branches from the branch that connects us to the external source. The same holds for the Vth node as well. Meaning, now, if we look at the LHS here, or the LHS here, this pertains specifically to this part of the network. Similarly, the LHS here and the LHS here, both of them again correspond to only this part of the network. So effectively, what we have done is we have on the LHS, we only have the branches which connects these nodes with each other only and not to the external sources. Now, putting this together, combining all of these current equations for each of the nodes, we can now get a more simplified form, which is equal to combining all of the above equations we get L times V1 to Vn is equal to 0 for most of the nodes and I naught for one of them and minus I naught for the other one. Where what is the L matrix? So again, what we can also do is we can write it in terms of the voltages and it becomes VA minus VQ times CAQ equals I naught. Similarly, this is round over Q VB minus VQ CBQ equal to minus pi naught, which gives us this particular expression. So note that this is very similar to the disagreement among the states that we saw before for the Laplacian. So this is how the Laplacian matrix appears in electrical networks. Similarly, a very straightforward application of the other rules that we know for electrical networks is for the power of a network, we can simply write the power dissipated in a network is directly given by V transpose LV, which is simply equal to summation of C I j Pi minus Vj whole squared, where I comma j vary from 1 to n. Remember that here V is a vector of voltages. Again, we're simply applying the formula for the power dissipated in an electrical network. We arrive at this expression, which is nothing but the Laplacian potential. So now we have seen where do we see disagreement or where do we see the Laplacian potential in a realistic network. Let's look at yet another interesting property that arises for undirected networks, which is the Kirchhoff's matrix tree theorem. what is this theorem and what does it mean? The Kirchhoff's matrix tree theorem says that, suppose we start by considering an undirected graph. G consisting of the vertex set V and edge set E. Then the number of spanning trees associated with G is given by any cofactor of L. Of the Laplacian matrix L of G, where obviously I comma J belong to 1 to N. We have introduced a few of the terminologies here. Before we get to seeing an application of this, let's quickly do a recap of a few things. The first one is the notion of a spanning tree. Let me quickly remind you what that means right here. Recap first. First thing that we'll recap is the notion of a spanning tree. Suppose we start with any network of this one. Given like this. See, this is what a network looks like. Let us consider yet another network from it, or two more networks for that matter. A spanning tree of the network, one of the possible spanning trees is this, where the root node obviously could be this or the other one. So is this the only spanning tree that we get in the network? The answer is no. We can construct yet another graph, which can look like this. We see that in this case, this particular node becomes the root node of a spanning tree. Meaning, given an undirected graph, we can have multiple different spanning trees. Which is a very important property. So the question is, how many such spanning trees can we get? And the Kirchhoff's matrix tree theorem gives an answer to that. But again, the answer is in terms of a cofactor. What exactly is a cofactor? Again, we'll do a quick recap of it. Before getting into a cofactor, let's quickly define what a minor is. So these are very basic things which we have read before, but just so that we are all on the same page, I'm doing a quick recap of it. So let's start with this. Given a square matrix, say P, minor Mij of P is the determinant of the submatrix constructed or achieved by deleting the ith row and the jth column. Okay, meaning let's just write matrix P with entries, perhaps P. This is P. P11 to P1n and Pn1 to Pnn. We can write some intermediate row like this, Pi1 to Pin. Now, the minor Mij would require us to first delete this particular row I and then some column j here. Then whatever matrix remains, we take a determinant of that, and that simply gives us the minor of the matrix. Now, cofactor is derived directly out of minor. What is a cofactor? Cofactor Cij of a square matrix P is defined as Cij is equal to minus 1 times I plus j times Mij, where Mij is a minor of P. And as before, I and j can vary from 1 to n. So now this is all that we need to know about what a cofactor is and what spanning trees are. So now let's try to understand the result that is shown here. It says that using the Laplacian matrix, we can directly compute how many spanning trees any graph will have. So let's apply this result to a specific example to understand it better. Start with this graph. This is the graph that's given to us. Let's quickly draw with the edges. Suppose these are the edges it has. To make it a bit more interesting, let's add one more edge here. Number the nodes 1, 2, 3, and 4. So this is the undirected graph that's given to us, and we're trying to figure out how many spanning trees it can have. Let's draw all of the possible spanning trees that we can see. In order to do that, let me copy our image and place it here and construct all of the spanning trees that are there. The first spanning tree that we can achieve is simply this. So now this is a spanning tree. Are there other spanning trees? Yes. Other spanning trees can be constructed in a very similar manner. This, we know that there can be 4 combinations of this variety. We have done, sorry, let me copy the original one. There can be 4 different combinations. The other one would be, so this. And there could be one more like this, which is simply this. So we see that there are 4 kinds of spanning trees that we have drawn here. Are there any other possibilities of spanning trees? So I would suggest the students to pause the video right here and try to figure out if there are any other spanning trees. So remember, when constructing a spanning tree, you must make sure that obviously it's a tree and must span all of the vertices in the network. Okay, I hope you've tried it now. So the answer is yes, there are few more spanning trees that can be drawn. Let's see what they are. So the next one could be, we can have something like this. An N shape. We can also have something like this. Like this. But again, it's a spanning tree, right? So are there any other options? Yes, in fact, there are exactly a couple more. What would they look like now? We can remove these two edges and we can do something else as well, which is this. Now we can remove these two edges. So what you observe here is that all of the spanning trees that we see here are in fact distinct from each other. All of them is indeed a valid spanning tree, meaning this network that's shown here has 8 spanning trees. So if we apply the Kirchhoff's matrix tree theorem, are we going to get that? Let's try to understand that. What we'll now do is, we'll try to calculate the lactation of this graph. In order to do that, let me copy this and paste it here again. It becomes a bit easier. And then let's quickly write up the adjacency and write up the lactation. We can directly write the lactation as well. It is degree minus adjacency. But okay, just so that all of us can follow, let me start by writing the adjacency. So here, node number 1 is connected to 2, 3, and 4. Node number 2 is connected to only 1 and 3. Node number 3 is connected to each one of them, that is 1, 2, and 4. And node number 4 is connected to 1 and 3. So this is what my adjacency would look like. And degree matrix is even simpler to construct. It is simply A times 1n, which would give, or we can directly add the rows to get the degree. First row simply adds up to 3. So it's this. And the second one has a degree of 2. Node number 2. Node number 3 again has a degree of 3. And node number 4 has a degree of 2. So the Laplacian matrix becomes 3 minus 1 minus 1 and minus 1. Similarly, minus 1, 2, minus 1 again, and 0. And it's minus 1 in all of these locations, and a 3 here, and minus 1, 0, minus 1, and 2. So this is what the Laplacian looks like. The theorem, let's read it again. It says that the number of spanning trees is given by any cofactor Bij, meaning we can take any of the cofactors. Just to keep things simple, let us take C11, which would mean we remove this row and this column. Then the cofactor is given by C11 equals, C11 equals minus 1 raised to the power 1 plus 1, and M11 is equal to the determinant two minus 1 0 minus 1 3 minus 1 0 minus 1 2, and this determinant is equal to, let me calculate it, plus minus 2. That's it. So this is equal to 2 into 5, 10 minus 2 given by 8. Meaning the cofactor here is 8. Meaning this implies that the number of spanning trees that we should get should be 8. Does it match what we got earlier? Let's quickly go back to all of the spanning trees that we constructed. We see here that we in fact got 8 spanning trees, which is exactly as predicted by Kirchhoff's theorem. Okay. So this was yet another interesting property that we get only for the case of undirected networks. Okay, so we'll end the lecture at this point today. In the next lecture, we'll continue discussing some more interesting properties associated with Laplacian matrices. Thank you.